Now that we've finished going through what an action potential actually is, it's time to figure out how that action potential moves. Now, I've kind of alluded to this in previous videos about movement of action potential down a neuron. But the process of propagation or conduction of an action potential is based on the coordination of the sodium ions moving and the voltage regulated sodium channels opening. So if we look at this image we see so far, right now, one thing to point out on this image, this is going to be the electrode right here. That's where that chart above it in the blue is reading. So if you notice, right now, behind it over here is where you have the red area. That's where the sodium ions are located. So it hasn't reached the electrode yet, hasn't reached where it's reading. So what we need to look at is how does it get from point A to point B? Because for an action potential to work, it has to be able to travel down the length of a neuron or length of a muscle. So there's action potential conduction or action potential propagation. It depends on what textbook you're reading as far as the terminology. So we'll start with the idea that we know an action potential is an influx of sodium into the cell. This influx is due to the voltage regulated sodium channels that opened. So right now, this red area has all these positive ions in it because that was the influx of sodium in there. We know that having all those sodium ions in there made that internal membrane less negative. So at that particular point, not where the electrode is, but where all these ions are, that area is up to around that positive 30 mark or so. But now all these positive ions in the exoplasm, they're not going to stay there. They're going to move down what's called the electrochemical gradient. What that is, electrical, chemical obviously. So the electrochemical gradient uses both electrical gradients and chemical gradients. We have this whole amount of sodium right back here in the actual neuron. It's a high concentration. It doesn't want to stay there by itself. We know diffusion means high to low. There's nothing, or very little I should say, not nothing, there's very little in that area I just circled. You notice it's still yellow, it's negative inside. So this high concentration wants to move over to that area. Also, the electrical gradient. All these sodium ions are positive. They want to move into this negative area. Opposites attract. So what's going to end up happening here is, as you move through, the ions travel down. They follow that electrochemical gradient. So if we look at these ions that are moving, we know that now they moved right here, right where the electrode is. So you can see how it shows up on the graph, we're depolarizing. But that's where all the sodium ions are currently concentrated. If you look just behind it, here and here, you're going to notice that internal environment is already negative. So back here where I circled, the voltage regulated sodium channels have already closed. The voltage regulated potassium channels have opened up to help reset this membrane back here. It's only this small little area right here where you can see the positive charges inside are. That's where you have the sodium ions. That's where the depolarization is. Just a small space. And that small space is moving down the membrane. Because those sodium ions, remember, want to move electrical and chemical gradients down towards the end of the actual axon. So really what's happening is we just keep depolarizing the next section, the next section, and the next section. Keep depolarizing in a wave-like fashion heading down. The impulse is always propagating away from the origin. That's because the positive ions want to leave the positive environment. They're not going to go back to where the positive environment was. So if we notice now, this area that was positive is now negative again. Instead, we've moved down the membrane over this area. Because again, all of those positive ions moved to match where the negative environment was, and high concentration moved to low concentration. Electrochemical gradients. As I already mentioned, potassium channels keep opening up behind this wave of depolarization. So you keep resetting. This entire area now is back to a negative environment. It's going through the repolarization, a little hyperpolarization, and then back to resting membrane potential. All ready to do this again. But there is a little snag. You can't immediately do it again. This was called the absolute refractory period. Now, the absolute refractory period is a very small window of time when you cannot, no matter how strong the stimulus, create a new action potential. So no stimulus, no matter what, creates a new action potential. So this AP here, that's action potential. All right, reason being, it creates separation. It makes sure every action potential has a little separation between it. This is important because we'll get to it later, but the idea is because every action potential is always the same exact height or amplitude, you must have some separation to look at the frequency. So that frequency we'll get to in a second, but there always has to be separation. And also make sure that they're traveling in one direction, start to finish. They're not bouncing around going back and forth. So it's always the origin to the end of that actual neuron. After the absolute refractory, there is what's called a relative refractory period. Now, this relative refractory, this area you could potentially get another action potential. But for this to occur, you must have a stronger than normal stimulus. So at the point where the sodium gates are closed, so we've passed depolarization, we're in repolarization, the point where the potassium gates are opened, repolarization, and repolarization is occurring, of course. So this is where the relative refractory period is. A very strong stimulus could potentially trigger an action potential. Here's the why it has to be a very strong stimulus. All right, this green is going to be your absolute refractory. You can't have anything. Reason being is all this way, all the sodium channels are opened. So you can't open the channels if they're already opened. So there's no way to cause a reaction. But when we start the relative period, right about here, at this point heading forward, you've already had the voltage regulated sodium channels closed for a little bit. You've had the voltage regulated potassium channels open for a little bit. That means we've already gone back partially towards resting state. So at this point now, there's room again to create a new action potential. You'll be able to see the difference between the two. If you tried creating one here, it would just mimic the exact same curve. So by starting lower down, it can create a new curve going off. Now the reason of why it's more difficult, why you need a stronger stimulus. Well, if you're up here in this part of the curve, you still haven't fully reset, which means you need a stronger than normal stimulus to trigger it to go again because you haven't fully reset. The ions aren't in proper orientation. The electrical signals aren't matching. If you're down here in the hyperpolarization, well, that means you have that much further to get until threshold. So instead of just the negative 70 up to negative 55, that 15 millivolts, now maybe you're down at negative 75, which means you have 20 millivolts to go. So that's why in the relative refractory, you have to have a stronger than normal stimulus to trigger a new action potential. But now, as long as you trigger it, so as long as you get an action potential to start, that's it. If you don't hit threshold, nothing. But if you do hit threshold, it's full out. There's no half action potential. There's no quarter action potential. If you hit threshold, you get a full action potential. But if you don't, even at negative 56, I mean, we're talking 1 millivolt off. But if you're at negative 56, nothing happens. You have to hit threshold, negative 55, for it to actually trigger and go off. So here we're looking at a little about frequency, as I mentioned before. This threshold down here didn't hit. If you notice, that stimulus is under threshold. But here, with threshold, we hit it. So the stimulus was strong enough to cross the threshold in this case. If you notice, there's some space between these action potentials. But now let's go for a stronger stimulus. This one went even further above the threshold. Because that was a stronger stimulus, it went further above the threshold. Look at the frequency. You're going to have a much closer frequency of action potentials. They're all the same height, same amplitude, but they're close together. So the higher the frequency of action potentials, the stronger the initial signal. So that signal was stronger. The lower the frequency of action potentials, the weaker the initial signal was, or initial stimulus was. So it's all looking at frequency, not the size, but the frequency. How frequent are they? Higher frequency, closer together, stronger impulse, stronger stimulus. Less frequency, there's more space between, means the signal, the impulse, the stimulus, it was weaker to start with. So the amplitude, the size of the action potential doesn't mean anything. It's all the same. It's all about the frequency. So action potentials, looking in how they're propagating, looking at how they're moving, looking in what they actually are as far as frequency, absolute refractory, and different channels.